So let's take a look at a multivariable function with a context wrapped around it. We'll look first at a joint cost function. So let's suppose that a firm or a company manufactures some item or commodity at two different factories, factory X and factory Y. And we'll use capital letters to denote the factories themselves. Then the total cost in dollars of manufacturing will depend on two quantities. Little x represents the number of items produced at factory X, and also it depends on little y, which depends on the number of items produced at factory Y. The cost function that you get looks like this. So C represents the total cost of production for the two factories combined, and then it looks like this polynomial function here, 2x squared plus 7xy plus 7y squared plus 800. Now I've just made that function up as an example. You can actually model this with more sophisticated software if you had actual data, but this gives us some example of what a multivariable function might look like in a context. So let's explore that a little bit. So our first question says, let's suppose, using the same cost function that we just saw, that the company manufactures 160 items at factory X and 120 items at factory Y. Then what is the total cost of production in this situation? So we start with the cost function, which was given to us in the previous slide. It looks like this. And then because we're given the value of little x to be 160 and little y to be 120, we can simply evaluate this function by substituting those two values into the joint cost function, and it looks like this. So there's nothing too complicated here except the order of operations, which dictates that you need to do any powers first. So for example, in the first term, 2 times 160 squared, you'd have to square 160 first and then multiply the result by 2. So if you follow the order of operations here and compute this, you'll end up with a total cost of $287,200. So this is a simple example of evaluating a cost function at given points. So the next kind of example of a multivariable function that we'll look at is called a production function. So the idea is as follows. The total output of a firm may depend on labor costs and capital investments. So we'll build a production function, capital P, that depends on two variables. Capital L is labor and capital K is capital. Of course, we're not using capital C. That is used for cost, so we don't want to confuse that. So we call this the production function. And a visualization would look like this. So think of this square or rectangle here as sort of a simple facility or factory that's owned by the company. And that company has invested a certain amount of money into labor costs and a certain amount of money into capital investments, capital costs. And so depending on those two investments, that particular company can generate a certain level of production, a certain number of items of production with those investments. So this is what we call a production function. So one important kind of production function is called the Cobb-Douglas production function, and it has this particular form. Capital P is dependent on labor and capital and is equal to capital A times labor raised to the power little b multiplied by capital K raised to the power little c. So capital A, little b, and little c are all positive constants that sort of determine the behavior of this function, and L and K are the variables. So this is what we call a Cobb-Douglas production function, named after two economists, Cobb and Douglas, who introduced it to measure the U.S. manufacturing sector around the year 1900. Here's an example of a production function that Cobb and Douglas produced while looking at their data for the U.S. manufacturing sector around the year 1900. P of LK is equal to 0.84 L to the power of 0.63, and k to the power of 0.3. So the capital A from the previous slide is 0.84, little b is 0.63, little c is 0.3. Now the meaning of those numbers is hard to explain here. They do have specific meanings, especially the powers 0.63 and 0.30. But for now we're just going to focus on making sure we understand how to work with these functions and then later how to optimize them. So let's suppose we want to find the production level when 10 units of labor and 20 units of capital are invested. The production function we're working with is the one we just saw. It's given here, 0.84 times L to the 0.63 times K to the 0.3. So to evaluate this function, we simply substitute 10 for labor and 20 for capital, and then we carefully do the arithmetic. And that's all it is. It's arithmetic. We follow the order of operations. We can use a graphing calculator or a scientific calculator or a spreadsheet. Whatever you choose is fine. Just make sure that you can get an accurate result, because you'll need accurate results when you put your numbers into WAMAT. Now, this is the value of that function at 10, 20. The way we would interpret that is we would say that when 10 units of labor and 20 units of capital have been invested, the total production is 8.80214 units, or items of production. Don't be thrown off by the 8.8 portion. Remember, this could be measured in millions, so this might be millions of items produced. So here's a three-dimensional picture of a Cobb-Douglas production function. In this picture, X represents labor and Y represents capital. And the corner of the room is actually sort of pointing at us. You can see 0, 0 right there. That's the corner of the room. That's the origin. So at that particular point, when there's 0 labor invested and 0 capital invested, our production level is 0. So it goes through the origin just like a revenue function did back in 2 dimensions. And then you can sort of see how that surface changes and moves as labor and capital change. So the vertical distance here, that vertical axis, is a measure of the production levels, and those production levels depend on the investment in labor and the investment into capital.